All right, so I'm going to be going over the Chapter 3 review worksheet here and just kind of talking about some of these problems. Um, Zombie outbreak in a small college town. Follow the following formula. So we have this formula right here. Population represented by P. The T is the number of days since January 1st. That is a bit of a wrinkle. Which the number of days since January 1st. So T1 would not equal January 1st because the number of days since January 1st, obviously that would actually make T0 represent January 1st, which is a little bit of a strange concept, kind of make things line up weird for some of these other answers, but something we need to pay attention to as we're answering these questions. So if T0 represents January 1st, how many zombies were there on January 16th? So this becomes a situation where we need to simply evaluate this function for certain T's, right? So if T0 represents January 1st, T1 would be January 2nd, T2 would be January 3rd, and I think you can see the relationship here, right? The date is one more than whatever T should be. So for this one, we're going to need to represent T equals 15. And for this one, we're going to need to represent T equals 30. I'm going to be using Desmos as my primary calculator and also to graph this function to sort of examine it. So I'm going to go ahead and open that up. So let's get Desmos live. All right, so I'm going to go ahead and type in the function we're dealing with. And I'm going to write it in terms of a function. So f of x instead of p and equals 30,000, 1 plus 600 e to the negative 0.08x. We'll just kind of verify that that was accurate. Looks good. Okay, so in this case, f of x represents population, and x represents the number of days, the time, the t variable. So I'm going to create a table to just to sort of help with my calculations, so I don't have to punch this in every time. So now our function at day 0, at t0, that would be what it was. We were supposed to calculate day 15 and day 30. So really quick calculations there for that. Essentially, we're just plugging in 15 for x, and Desmos is doing all that calculation for us. Now, the second question is asking us to figure out how many days will it take for there to be 20,000 zombies. So we could kind of keep plugging things in here and see where we get there. 25,000. At this point, we're only at 2,500. So I think we need to go out a bit further. Maybe 200 days. Okay, so 200 days, we've surpassed that amount. So obviously, you can see this sort of guess and check method is not ideal. It's going to be somewhere between 50 and 200. So what I'm going to do instead is I'm actually going to change my x-axis from 0, not negative 0, to, we'll just go with 200 days, since that seemed like a not too unreasonable number. We can count those by 10. Our y-axis looks like that's near 30,000, so I'll just give it some space and I'll say let's go up to 40,000. Okay, that should give us a good view of our graph. Now we can, oops, I zoomed out again there. Let me zoom back in. Well, that should be fine. That's fine. So we're looking for when it reaches 25,000. We could kind of drag this around until we're close. That's pretty close. Looks like it's sometime around 100 days. But let's actually create a horizontal line there at 25,000 just to find the exact intersection point. One more 0. So this line is sort of representing 25,000. So we can see as the days are moving forward, it's approaching and approaching and approaching it until finally at 100.08 days. So right around 100 days, it reaches that 25,000. You need to be able to examine this graph to do this, or solve it, although solving it would be much easier. I'm really looking for a problem like this for you to actually graph the function and kind of work with it in this manner. So we can kind of take our answers here. On the 16th, we would have around 165 zombies. On the 31st, we'd have 541 approximately. And to reach 35,000, it would approximately be around 100 days. Round those answers to whatever's appropriate. In this case, I was just going to use whole numbers. All right, let's go ahead and go back to there. All right, our next one, we have the half-life of iodine-131 is 8.07 days. It's probably important. We'll use that here. How much of a sample of 800 grams will remain after 3 weeks? All right, let's examine this half-life formula real quick. So NT represents the amount of the substance remaining after some amount of time. N naught or N sub 0 is the initial quantity. So that's actually this amount, the 800 grams. Time elapsed, that's our 3 weeks. This is our T. And T sub 1/2 is the half-life. So this is our T sub 1/2. One important thing here is these two need to be in the same units. Weeks and days need to be sorted out. So I'm going to put them both in days. So 3 weeks is also 21 days. So this really just becomes a matter of evaluating this function for 21 days. So N21 would be equal to 800 times 1/2 to the, 21 over 8.07. And for simplicity, I'm just going to take this to Desmos and do a little calculation. And I believe it says to round to 3 decimal places. So we're going to get 131.747. Yeah. So there would be, after 21 days, we would have 131.747 grams remaining. That would be our answer there. Just using a function, taking the information that's provided to you, kind of turning that into something we can evaluate. All right, let's go ahead and move forward. All right, so then here, from here on out, we have our basic logarithmic to exponential relationships, understanding how we can kind of convert those back and forth. So I'm just going to write our basic rule for that. So y equals log base a of x can be converted technically back and forth as a, same base as the logarithm, to the y equals x. The thing that's happening here that's a little bit different is the bases are the same. The input of the logarithm becomes the output of the exponential, and the output of the logarithm becomes the input of the exponential. All right, so let's go ahead and solve these by converting them. So we have log base 2 of x equals 6. So that's a simple conversion. Base 2 for exponential to the 6th power equals x. 2 to the 6 is 64 equals x. Pretty easy to do that one. This next one we could solve without. We could just kind of simply evaluate our logarithm, but we're going to go ahead and convert it just to do it that way. So this becomes the same base to the x equals 125. So we need to figure out what power of 5 is going to give us that. And the answer to this is to the 3rd power, because we can always rewrite 125 as 5 to the 3rd. 5 times 5 times 5. All right, and then our next one, this one's actually a fairly tricky little one. So if I rewrite this one, this becomes x to the -4 equals 1 over 16. Using exponent rules here, I actually can write this as 1 over x to the 4th equals 1 over 16. There's a lot of different ways that I could then simplify this. I could do cross products if I wanted to get 16 equals x to the 4th. However I want, that's going to end up being the equation that I get. And then to finally simplify this would be to use the 4th root, right, to get rid of that and to do that on both sides. So that gives me that x is equal to, now technically the 4th root is actually plus or minus 2. We have both a principal root and a negative root. But keep in mind here, this variable in our original equation is the base of a logarithm. It actually can't be negative. So our only solution, our only valid solution here is x equals 2. That one was a little bit trickier. And then the last one here is a natural log. So remember, natural log is log base e. I can rewrite it this way if I want to, but I can just kind of keep that in mind also. So converting this, we actually get e to the 6th equals x. We could multiply that out and get e to the 6th, but I'm just going to leave my answer in terms of e. Okay, I'm going to clear this. I'm actually going to clear selectively, so I'm going to clear everything but the close. So this was y and this was a. Okay, so the next set of problems here, we're going to solve by kind of doing this in the other, or sorry, we're not going to solve them. We're going to just simply convert an exponential into a logarithm. So base is going to be e, so remember that means that we're doing natural log. The output of our exponential is what we're actually going to be putting in our log. And since e is an irrational number, we're always going to get a non-terminating decimal here, but we'll round it to that point. And that would be equal to the input of our exponential, -4. So that's the relationship we'd want to be able to write there. Next one, a little bit easier. Log base 4, remember same base, of this 1024 is going to equal x. There we go. We could go ahead and solve this if we wanted to, however we wanted to. 1024 might be a power of x. I know that we can solve this to get an answer here. 1024, 64 times 4. I'm not going to do that one right now, but we can actually probably get a solution to that if we were careful with our exponent rules. All right. Last one here, a couple applications of using compound interest. This just becomes a matter of making sure we plug in numbers in correctly into the compound interest formula and knowing when it says it compounds quarterly or monthly or semi-annually, what those things mean. So quarterly means once every quarter of a year. So that's going to be 4 times per year. Monthly means once every month, which would be 12 times per year. And semi-annually is once every half year. So that's actually 2 times per year, right? All right, so then we can calculate these and see what we get, right? P is our initial investment. R is our interest rate. Remember, that's a decimal. So we take our percentage and divide it by 100, or we move the decimal place over 2 spots. Whatever you do there, be careful to make sure your interest rate is represented appropriately. Number of times it compounds actually goes in 2 places, so quarterly, monthly, annually. And then the number of years for most of these that our investment takes place. Again, it's just a matter of substituting these values and evaluating appropriately. So our first one is 2,000 times 1 plus 4.5% is 0.045, right? We took that decimal, moved it over twice, or divided by 100, whichever method you prefer. We're compounding it quarterly, so this becomes 4 times, and it's in a period of 15 years, so 4 times 15. We just evaluate this. It's not too difficult. I'm actually going to write out all 3 before I do this because I'm going to use Desmos for the evaluation. Second one, same idea, $1,000 investment. Interest rate is 1%, so 0.01. We move that decimal place from right next to 1 to over 2 spots. Compounded monthly, 12 months, 12 times a 10-year investment. And then the very last one here is a $5 principal investment. So that's very little. Interest rate of 6%, 0.06, and compounded semi-annually for 300 years. Okay, it's a pretty crazy long investment, but that's it. And let's see. If you did it this way, take a prediction on which one you think is going to have the most. I mean, we started with the most here for 15 years. I figure if I had to order these, this starts with the most, and it's more years than this one. So I think this one's going to give me more than that, and the interest rate's higher. So yeah, definitely this one's better than this one. This one, though, because it's 300 years, actually might end up being the most. Anyway, let's use that calculator and let's just type these in. 2,000 times 1 plus fraction 0.0454. And as an exponent, 4 times 15 is 60. Okay, there we go. That's that one. 1,000 times 1 plus fraction 0.01 over 12. Exponent is 12 times 10 is 120. Okay. And then last one, 5 times 1 plus fraction 0.06 over 2 to the 2 times 300 is actually 600. Okay, yeah, wow, that one is by far the biggest. Keeping in mind we are rounding for money here. So our first answer is right there. Cut it off at 2 decimal places. $3,913.29. This one here is $1,105.12. Yeah, no rounding up. Here we have $251,944,468.32. We'd have to round that up. So there we go. This one was the most. Small investment, but a very long period of time. All right, and that's it for that worksheet. Good luck, guys. Send me emails if you have questions, and have a good break.